This is a video on the second partials test. The question states, locate and classify the relative extrema of f of xy is equal to x cubed minus y squared plus 6xy minus 27x plus 2y plus 5. So we're going to use the second partials test, which tells us whether we have max, min, saddle points, or the test could fail. But before we do that, we need to locate the possible relative extrema of f of xy. Since f of xy is a polynomial in x and y, which is differentiable, there won't be any critical points based on non-differentiability. So the only possible relative extrema are when the gradient of f of xy is equal to 0. In other words, when the partial derivative of f with respect to x is equal to 0, and the partial derivative of f with respect to y equals 0. So let's find those partials. F sub x is equal to 3x squared plus 6y minus 27. I set that equal to 0. And now let's find the partial derivative of f with respect to y. F sub y equals negative 2y plus 6x plus 2. And I set that equals 0. So I have two equations and two unknowns that I need to solve. So I first use the second equation, and I solve for y. I can divide by 2, move the y over, and I get that y is equal to 3x plus 1. So now I substitute 3x plus 1 in for y in the first equation. And I get 3x squared plus 6 times parentheses 3x plus 1 minus 27 equals 0. So let's divide by 3 first. So this 3 goes away, the 6 becomes a 2, the 27 becomes a 9, and then 2 times 3x is 6x, 2 times 1 is 2, minus 9 is negative 7. So what I got is that x squared plus 6x minus 7 is equal to 0. And this factors as x minus 1 times x plus 7 equals 0. Or in other words, x is equal to negative 7, or x equals 1. So that's my x. Let's find our y by using y equals 3x plus 1. 3 times negative 7 is negative 21, plus 1 is negative 20. And 3 times 1 is 3, plus 1 is 4. So I get 2 points, negative 7, comma negative 20, and 1, comma 4. And those are the points where there could possibly be a relative extrema. So now let's find out if there are relative extrema, and if there are they maximum or minimum? And maybe we have a saddle point that isn't either, but still interesting. So to do that, I take the second partial derivatives. I take fxx by taking the partial derivative with respect to x of fx, and that's 6x. Then I take fyy, the partial derivative with respect to y of fy, and that's negative 2. And then finally I do the mixed partial derivative, so I can find the partial derivative with respect to y of fx, and that's 6. Or by the way, I can take the partial derivative with respect to x of f sub y, and that's also 6. The mixed partials are always the same in either order. So I get fxy equals 6. So now if you remember, the second partials test involves this d function, which is fxx times fyy minus fxy squared. So we take 6x times negative 2 is negative 12x minus fxy squared, or minus 36. So you get that d is negative 12x minus 36. So now I plug in the points. I plug in x as negative 7 and y as negative 20. Here we just have an x. So if x is negative 7, negative 12 times negative 7 is 84. 84 minus 36 is a positive number. So we could say that d of negative 7 comma negative 20 is greater than 0. When D is greater than 0, we either have a relative max or relative min, depending on fxx. So fxx, when x is negative 7 and y is negative 20, I plug in negative 7 for x, and I get negative 42. So in particular, fxx of negative 7 comma negative 20 is less than 0. So if D is greater than 0 and fxx is less than 0, then we have a relative maximum. So now let's find what this critical point 1 comma 4 is. So I plug in 1 comma 4 into D. So here x is 1 and y isn't in D, so I don't have to worry about it. And I get negative 12 times 1 minus 36 is negative 12 minus 36 is a negative number. So D of 1 comma 4 is less than 0. When D is less than 0, we have a saddle point, regardless of what fxx is. So I'm ready to state my conclusion. I can conclude that f of xy has a relative maximum at negative 7 comma negative 20 and a saddle point at 1 comma 4. And I'm done with the problem.